Okay, so uh, let me explain what it is that I'm working on today. Okay, so something that I've wanted to make for a while is a bouldering simulator. In other words, a sort of something close to a video game where you've got a little character you can move around on a wall with holds on it, and your job is to plan a route that will be, the most efficient or something like that. Well, at first, just to keep things simple, I, what I need first of all is like a little solver. So the idea is, I draw the holds on the wall somewhere. For now, I'm not going to worry about the shape of the hold and which way you can get the most like normal force, friction, this, that, and the other thing. Like for now, I'm just going to treat this as like a fixed point that you can rotate around in any direction. But let me be a little bit more precise. The constraints at each of these points is, well, okay. I haven't actually set up this problem, so let me do that now. So we've got the holds on the wall. Each one has a particular position. Also, this is distracting me, this thing down here. I want to, I guess I can just do this. Okay. So for what I'm going to do right now to keep things simple is I'm going to model the climber as just a mass sitting here. And we're going to have arms and legs. Okay, well, ignore the fact that this leg is longer than that one, but let me just draw ahead so it doesn't look too weird, but I'm just going to model a point mass just right here in the middle of the person. Now, each of these holds can apply a force, and for now, like I say, I'm going to keep things simple. It can apply a force in any direction, and I guess we're also going to allow it to apply a moment, because in principle, you have some friction on this hold that lets you not twist around it, maybe. So each of these, so let's call this, I guess we'll call the holds like, I don't know, H1, or, man, I need a different font, maybe this, H1, H2, H3, H4. And so for each of these, we have F2 and I guess I'll call it T for, I guess, capital T2, right, for each of these. And each of these is a vector. I'm not going to draw the arrows for each one. I'm just going to draw it here. And, we have what we're going to enforce for now is the constraint that the sum of all the forces is equal to 0, and that the sum of all the moments. Well, let's do T sub, I don't know, I guess I need a name for this. Let's call it because the sum of all the moments around a particular point, right? A moment has to be measured around a point. So we could take, like, maybe we could take all the moments as measured around the center of mass, for example, something like that. By the way, I'm not modeling right now the fact that if you bend your legs in a particular way, your center of mass is going to move. I'm not doing that. I just want to try something simple and see if I can get it working. Anyway, the point is that we're summing the moments around a particular location, so I'll just call it L for location. So the sum of the moments around a particular location is 0. But here's the problem. Given a particular set of holds, I need more drawing space. Can I do this? Oh, wait, no. I can't. hold on. Oh, here we go. Okay. Given a particular set of holds, there's more than one way that you could be positioned on it, right? Like maybe you could be like this. Well, you get the idea. Okay, this is not maybe a comfortable position to be, but well, I guess I could draw this arm a little better. Maybe this arm would be a little straighter. I said straighter. Okay. So it is possible. There's actually probably an infinite number of ways that you could be situated on these holds and still maintain these two constraints. There's actually a number of other constraints, and this is where the problem is starting to get more challenging, right? Because we could have constraints of like, fi is less than some number. So for example, maybe this hold has a maximum, or your hand has a maximum amount of force it can tolerate, right? Or we could also have stuff like, the angles of your limbs or something. So I could call this maybe like θ2 or something. Anyway, we could have stuff like θi, is in some range. So we have like let's pick some random number. 15 is less than θi is less than 85 or something, right? I have no idea if these numbers make any sense, but the point is you can't bend your arms as freely as you want. We also have that, I'll just write it in words here. Length of arms is constant. Length of legs is constant, etc. And this is really where I'm starting to have trouble. It's one thing to just solve the statics problem and even maybe to pick one of the infinite number of solutions. It's quite another to also enforce a bunch of these other constraints. I just have no idea how to do it. I tried looking it up, but all I can find are these abstruse like mathematical papers that I can't understand like for the life of me. Or I guess I could sit down and really think about it, and that might be what I have to do eventually. But there's got to be something simpler, Anyway, what I am thinking of doing is the following. This is my hypothesis, right? It's what I'm going to try to do right now. We're going to use Gaussian eliminations. Let me write this down. Idea. Use Gaussian elimination to actually, okay, it'll be easier to explain the idea after I set up the math. So these two constraints, or I guess these, equations, right? These equations would lead to something that we're going to solve. So we're going to have some matrix times the positions, all right, times, so I could call this H1x, or sorry, F1x, F1x, F2x, F1y, F1z, etc., all the way down to the torques as well. So down to T4x, T4y, T4z. Right? We're going to have some matrix times our things that we're solving for, which is the forces and torques on each of the holds. It's just some matrix is equal to 0, right? Which I guess I could write like this. And this is going to have infinite solutions in the general case. So the idea is we're going to use Gaussian elimination to write like to rewrite this as, we're going to have one thing that we actually need to solve, right? So there will be some limited number of degrees of freedom here, I think. So let's suppose there are 3 degrees of freedom. I think it might be possible. Okay, I don't know if this is true, but so let's suppose there are 3 degrees of freedom. I'll write it out. This is still unconfirmed, so we might have more or less. Then what I want to do is I actually want to figure out, so let's give this matrix a name. I'll call it, I don't know, S for sum of forces. And we're going to make a new matrix here, which is going to be smaller. And I'm going to call this, I don't know, R for reduced or something. And the vector here is just going to be, I could call it ABC for generality, in the sense that, well, if there's only 3 degrees of freedom, then these are just arbitrary variables that you can put anywhere you want. But actually, I think it would be nice if we can reduce it to 3 degrees of freedom, that maybe it should be one of the points on the person's body, so maybe the center of mass would be a good point to choose. Well, yeah. I'll write it like this, equals 0. And then maybe we'll say ABC is equal to mx, my, mz, right? Maybe we'll say that. Well, I guess these are column vectors. So fine, there. So that's the first thing we need to rewrite. So I think if we are able to reduce this matrix such that there's only 3 rows left in it, then it should be possible to basically have a transformation matrix between this thing and ABC, right? So what we're going to have is, whoops, ABC is equal to some matrix, I guess I'll call it T. So it'll look something a little like this. Times this guy. And we could even go one step further. I didn't mention this before, but even if, let's suppose this did have a unique solution and we solved it, we would still be interested in knowing the internal forces and bending moments everywhere around the body, because that will tell us how useful of a position this is to be in. So I'm starting with this idea of reducing the dimensionality to its minimum, and even more so, reducing it such that it's actually a point that maybe you can drag around yourself, like as a human being. And then all these other points of interest, like how much force is on the holds, how much force is on your joints, will come out of it. And actually, all these other constraints will be things that we can test. So we have this this final matrix here. Now wait a minute. Hold on. Wait. I think there's something wrong here. I've never been that skilled at linear algebra, so just please bear with me. If there's 3, this doesn't look like 3 degrees of freedom. This looks like solving a linear equation that has no degrees of freedom. where are the degrees of freedom in this expression? Man. Okay. I think what I need is to do an example of Gaussian elimination. So sample problems. Sure. Fine. And I need one that has infinite solutions. I just need to remember how this works. Oh, geez, this looks pretty spiffy, this website. Okay, here's an example of one that doesn't have a unique solution. Oh no, it does have a unique solution. Well, that's not true because some of them have infinite solutions. I think we're going to have to concoct our own problem here. Let's just see if we can make one up. Geez. I don't know. Let's do an obvious one here. Let's do 1, 1, 1, 2, minus 2, 2, 3, 3, 3. Not to scale. Well, I guess this is something I always did wrong. Like something I always realized when I was doing my lineage homework back in the day is that you should draw the numbers first and then draw the brackets. Anyway, times, x, y, z equals. And in general, this right-hand side can be non-zero. So let's just call this, I don't know, ABC. Okay, so if we, let's not overthink it here. If we put this in reduced row echelon form, what we get is, oh my goodness, it has been a very, very long time since I did this last. Okay. Oops. Whoops. Whoops. Okay, hold on. I'm not going to bother with the brackets. So this is, actually, I think I will. I changed my mind. It makes it easier to delineate them. So first what we do is we subtract 2 times the first row from the second row. So so then what we get is this. This becomes a 0 as desired. This becomes minus 4. This becomes a 0. And this becomes b minus 2a. and then here we do minus 3x, or minus 3 times. It's not x, it's times. Minus 3 times. And then we get, I mean, it's not a crime to be bad at linear algebra. Okay, get off my back. Oh, wait, this has no solutions. Well, not necessarily, because if c minus 3a is 0, if we assume c minus 3a, or if, I'll just put if instead of assume. If c minus 3a is 0, then we do have solutions, I guess. So what does this tell us? Oh my god, dude. I cannot believe how little of this I'm able to remember. I think what ends up happening is that your final solution is a linear combination of vectors. That makes sense to me. So how do we find out what is the basis, or like what vectors form that linear combination? Man, I'm thinking here. So, what if we try the vector? So this is, I'm trying to think how to automate this, but for now, what if we try the vector? Okay, let's put numbers on here. Let's just say, I don't know, just so that we have something concrete to work with. So I don't know, let's just say that this is friggin' 7 and this is 5 and then this is a 0, because otherwise it wouldn't have any solutions. So what if we try okay, let's make this 4. Anyway, so if I put the second number as -1, then that'll solve this. And then if that's -1, then these two have to add up to 7. So let's do 2 minus 1, 5 as a solution. So this works. Now, how do we get a computer to come up with this? I'll think about that in a second. But for now, I just sort of did it in my head here by sort of guessing and checking. So yeah, that makes this row work. And oh wait, it actually has to be 14. It's 14, yeah. No, hold on. -1 times 1 is -1. So these two have to add up to 8. Okay. So yeah. So if I do 3 minus 1, if I do 3 plus 5 minus 1, I do get 7. So okay, that's good. But there's another solution, which again, I'm just doing this like, I'm not doing this in any methodical way. I'm just realizing, well, I picked 3 and 5 here arbitrarily, but I could have done 0, -1, and 8, and that would have also worked. And so actually, it seems a little more useful to actually do it like this, like that. So both of these are solutions, and they're not collinear. So any solution to this system will have the form, so let's call this capital A, well, I don't know, let's call this x1, or I don't know, let's call this x and let's call this y. So any solution, maybe I'm being too persnickety here, but so any solution to original system can be written as x, shoot. Now wait a minute. It's not just any arbitrary linear combination of x and y. It's like ax plus by such that a plus b equals 1. Ugh, man. No, that doesn't work. Oh, no, that does work. That does work. What? So actually, there's really only one degree of freedom here. So in reality, any solution of the original system can be written as, or in other words, ax plus 1 minus ay. Does that work? Let's just make sure that works there. Try a equals 100 or something. So then 800. So that means 1 minus a equals negative 99. So we have 800 minus 100, 0, plus, this doesn't make sense, 0, 99, negative 92, 792, I mean. And then this is equal to 800, negative 1, negative 792. Oh, look, this does actually work. Or does it? Oh, yeah, it does work. Yeah, if I add up these three things, I get 7. And if I take negative 4 times the center one, I get 4. So what's the pattern here? What's the method here? Like, how could I come up with these without me just in my head thinking like, oh, I think that would work? Okay, so here, the computer solves for x and y, which may not have any geometric or physical meaning in the context of the problem. But the user is going to pick A. They have that degree of freedom to do whatever they want with. So I guess maybe if we were to try writing something like this, solution, any solution is I'm trying to, because I know that there's going to be, I'm trying to figure out what's wrong with this thing right here. There's something wrong with it. I'm just trying to understand what. I think in reality, this isn't zero. I think what we have is that on the right hand side here is oh, okay. I think no, wait a minute. Yeah. Okay. I think this is what we want. But I already wrote that, didn't I? In other words, these are your degrees of freedom, and there is some transformation matrix, which I guess I will end up calling this T. So these are your degrees of freedom. You control this. There's some transformation matrix T that spits out this vector here such that when you plug it in here, you get 0. So what we want to do is obtain T given S. Does that make sense? And how does that work down here? What is T here? Right? So our final degree of freedom is just a single number. So we have T times like the single number A. Well, okay, let me write it like this. So the single number A, and this is going to be equal to I gotta figure out how big T is. So we have just a one element vector, and this is equal to some 3 element vector, which I'll call I don't know, x1, x2, x3. What did I call it up here originally? X, Y, Z. Okay, so I'll stick with that. X, Y, Z. So therefore, this matrix T has to be a 3x1 matrix. And we have that T is equal to what? But I shouldn't have called this X, by the way. Let me rename this real quick. Well, it's, yeah. Because I need this Y component here to be -1, no matter what A is. So do I need, man, I wish I was better at linear algebra. So do I need like plus, I don't know, let's call this B for bias. So we have t is equal to one, 0, -1, or no, 8, 0, wait. Yeah, I know. Yeah, 8, 0, -8, and yeah, okay, I think this is it. Yeah, 8, 0, -8, and B is equal to 0, -1, and 1, right? I know, 8. It's 1 minus A times 8, which is 8 minus 8A. I mean, I just kind of feel like I'm just guessing and checking and just figuring this all out, but you know, maybe I do need a B term here, you see. And I can't quite understand why. Why? Maybe there is no reason why. I don't know. So here our t is 8, 0, -8, and our b is 0, -1, 8. Oh, man, I don't know what I'm doing. I don't know what to look up. Maybe I just got to think about it harder, and I'll figure it out. Well, okay, if in this reduced matrix, like let's say we had an upper triangular matrix, for example, okay, then we could do back substitution. And then we would just get, you know, a single unique solution, right? But when we have these basically indeterminate rows here, we don't get a unique number. We get like x or something, or what did I call it? Z. Like here, instead of getting an actual number here, we just have an unknown or a free variable z. And then here we get that y plus 0z, or -4y plus 0z equals 4. So y is equal to -1. And then x is equal to so x plus y plus z equals 7. So x is equal to 7 minus y, which is just 1. It's always negative 1, so it's 8 minus z, which is exactly what we had before. So oh, I think I see it. I think I see it. I think I see it. Okay. Let's take this. Okay, let's say in the reduced row form, we just have an upper triangular matrix. So now I'm running out of variable names here, so just forgive me. I'm just going to say A, B, C, D, E, and F. And then here I'll just call this, jeez, I don't know. I need more variables. GHI, fine, whatever, it just doesn't matter. So in general, let's say that this is our reduced row form, then what we have is the solution is z equals I over f. But if I and f are 0, then z is indeterminate. And then here we have y is equal to h minus ez over... Oh, something I totally forgot about. I forgot to normalize this row. So actually, in general, these are just going to be 1. Well, not necessarily. It's either 1 or 0, but let's just suppose it's 1 for the time being. So z is equal to I. Y is equal to h minus ez. And x is equal to g minus by minus cz. Or in other words, we have we just have this, and the more indeterminates we have here, so if here, if this 1 was a 0, then we would have a second indeterminate, and then so okay, what I'm trying to get at here is that this here is B, and the rest of this is, I'll just draw it like this, the rest of this is T, I think. Right? Right? Oh my god. Why is linear algebra so difficult? I've never understood it fully. Yeah. Because there's other problems that I'm going to face, which is that there's this concept of pivoting, which I need to deal with. And then there's singular value decomposition. I literally don't know anything except that it's called singular value decomposition, and it's meant to help with numerical stability for matrices that are close to undetermined. But I have no idea what's involved in the method or anything. Oh, wait a minute. I just realized something. if we plug in this expression for that, then our final expression is so actually I think oh man. Man, I'm thinking. uh, all right, let's try system of equations, dimensionality, reduction. Oh, DMG, it's got a TLA, it must be good. I never heard of this. What? No, I don't think this is what I need. Fine, let's figure out what SVD is. It is a factorization of a matrix to generalize, oh, here we go, the eigendecomposition of a square matrix with an orthonormal basis to any non-square matrix. It is related to the polar decomposition. Okay, let's just give this a shot. Specifically, the singular value decomposition of an m by n matrix is a factorization of the form m equals u sigma v star. Oh my god, dude. Where u is an m by m unitary matrix, whatever that means. Sigma is a rectangular diagonal matrix, which actually I think I do know what that means. It's a diagonal matrix. V is an m by n complex unitary matrix, and v star is its conjugate, transpose. Such decomposition always exists for any matrix. If M is real, then U and V can be guaranteed to be real orthogonal matrices in such context. The SVD is often denoted U sigma V transpose. The diagonal entries are uniquely determined by M and are known as the singular values of M. The number of non-zero singular values is equal to the rank of m. That's interesting to me. I believe the rank is however many degrees of freedom you need to solve the equation. Or maybe, I can't remember. The columns of u and the columns of v are called left singular vectors and right singular vectors of m respectively. They form two sets of orthonormal bases, u and v, and if they are sorted so that the singular values with value 0 are all in the highest numbered columns or rows, the singular value decomposition can be written as a bunch of dot products. No, a bunch of outer products. Fascinating. The SVD is not unique. It is always possible to choose a decomposition so that the singular values are in descending order. In this case, sigma, but not u and v, is uniquely determined by m. The term sometimes refers to the compact SVD. Okay, this sounds like what I need. This sounds like what I need. Okay, so, excuse me. If m, illustration of the singular value decomposition, the action of m indicated by its effect on the unit disk d and the two canonical unit vectors e1 and e2. Okay, so it seems to leave x alone and kind of stretches and tilts y a little. The action of m left, the action of v star, a rotation on d, e1 and e2. The action of sigma, a scaling. The action of u, another rotation. Yeah, okay, so I understand the concept of scaling. I wonder if 3 Blue 1 Brown has SVD videos. This is just this. What the fuck is a unitary matrix? Like, God. Okay. linear least squares. Pseudo inverse. Okay, let's see this. Oh, man. How on earth am I ever going to get this? What is Hermetian? Like, who? Uh, why is linear algebra so abstruse? Like, it should be so simple. I mean, I guess I should expect this. Trying to learn math from Wikipedia is mostly impossible. One second. Okay. So I need to do this, and I don't know how. I have like the vague notion that, or at least earlier, I had the vague notion that Gaussian elimination was the right way to do it. But then there's this singular value decomposition. But I'm a little confused because this is just factoring the matrix. But what I was trying earlier, I needed this extra like addition, right? I couldn't just factor it as just t. I needed this b vector. And I don't understand how that would manifest itself from this. So I'm confused. Something doesn't make sense here. One of these days I'm gonna write like a linear algebra tutorial that doesn't, I don't know, man. There's just something about linear algebra just like pisses me off. Every time I try and do anything with it, it'll be like, oh, well, just compute the determinant and then square the eigenvalues, and then, it's, you need the Hessian pseudo-inverse. It's like, what is any of that? Like, anyway. So, if this is my matrix S, all right, let's at least for this problem here, and I arbitrarily picked 7 and 4 here, so maybe let's just pick A, B, and C such that it works out to this example like I did earlier. So I think that means A has to be 7, and B minus 2A is 4, so this has to be 18. And then C minus 3A is 0, so this has to be 21, I think. So we have this problem here. Okay, so actually it's not just given S, obtain B and T. Actually, I mean, I've written this as the 0 vector, but in principle this could be any vector. So here my S is this, my V is this, and what I did over here is I figured out that T and B were this. Why? How did I get that? Well, after reducing the matrix, I ended up with something like this, where this 1 here was actually 0. I think T and B are not unique, actually. Because if I try to do and do, well, okay, let's just write down, so here we did RREF, I think that's the name of the operation here, reduced row echelon form. Let me just delete these scribblings here. And actually what we got here was 0, 0, like that. So what does that tell us? Well, man, I don't know. So here, B is 1, C is 1, E is 0. Actually, let me copy paste this. And just leave this up here as like a note. So we did reduced row echelon form on that. So this GHI is 740, and I was saying let's make that B. So let's see what happens here if we do that. If we make B 740, that doesn't make sense. That doesn't make sense. Well, no, it does, because we're trying to find X, Y, Z. We're trying to find X, Y, Z as, yeah, that's right. It's 740 plus some linear combination of B, C, and E. Now, E happens to be 0. But actually here, so this T, well, no. B, C, and E are constants. What's not a constant is X, Y, and Z. So if we let Z be free, if we're letting Z be free, then the bottom row of T is a 1. And the next one up, no, this doesn't make sense. Because I had 1 degree of freedom. So how do I express this with 1 degree of freedom? Well, Z is free, which means Y is a function of Z, which means X is a function of Z. So man, I don't get it. I don't see what I'm doing. What am I missing? I know it's got to be something simple. Oh, there's somebody in the chat. No, this is a personal project. I think they're gone. I don't know anything about VLSI. I guess that's what I get for making this public, but anyway. Man, I really wish I knew what I was doing. I really wish I had a hint. But I don't. I have no idea what to do, so I'm just gonna just keep fighting with it and try something else. So one thing I'm noticing here is that so long as this expression is 0, if this is 0, and by the way, it needs to be that, then we can use SB to satisfy right-hand side. But this seems to be defeating the purpose. The whole purpose was that, no. I guess we don't need to have this be the actual forces. I don't care what this expression is. I really just care that my original expression is satisfied. So maybe what I need yeah, because b, I'm going to solve for it, it's just going to be a constant. So actually, it's not if this is 0, this has to be 0. This has to be identically 0, no matter what a, b, and c are. Now what'll happen is, so this, I think we're just going to get rid of that, because there will be some way to compute this vector based on a, b, c. But that will only be true, I think, if we can make this identically 0, this expression here. Because then that means that yeah. Because t, a, b, c will make a vector of the same length as this f and t vector. And it won't be able to satisfy the the heterogeneous equation, because we're going to make this identically 0, this expression here. But it's okay, because we'll just fix that up with a b vector here that I don't even really care about, I guess. Yeah, okay, so b is... Well, no. Wait a minute, I'm back to the same problem. Finding b is to solve this equation. Man. All we did is we kicked the can down the road. So actually, maybe I shouldn't have crossed this out like I did before. Maybe this is actually more important than I thought. But I think what this is telling me, this line of reasoning over here, is that I can't have this. Because if this is a constant and that's a constant, this has to be identically 0. Or, well, does it? Is it possible for this to be for this to become a constant but not be identically zero? Is that possible? But then even if that was possible, then I would still have to solve this. So what if I force this to zero? Is that possible? No, of course not. Because if this was equal to v, then if I plug in 2a, 2b, 2c, then, by linearity, the outcome's going to be 2v. Right? Right? I'm not losing my mind here. We can't force this to, or we could, even if we force it to zero, we have the problem that if I scale this vector, then it's going to scale the output, and so I can't, like I don't have degrees of freedom, even if I write it like this. Oh, man. If I multiply these two matrices together, I think my initial thought here is wrong. Like I think I went down the wrong path at the very beginning. No. Wait a minute. I think because the whole reason why this is possible, the whole reason why I kind of wanted to do this is because it's not just one vector here that solves this equation. There's an infinite number of vectors that solve this equation. How many? In other words, what dimensionality? Well, I'm assuming it has 3 degrees of freedom. Again, we'll have to confirm that. Which means that this vector is actually equal to some b plus some linear combination of, I get it. Yeah, okay, so these are actually the null space basis, right? So this is the basis of the null space of S. So anything I do here will, yeah. So this is identically zero. Columns of T should be basis of null space of S such that this is identically zero. And this B is any arbitrary solution So, I mean, I do. I think I might have jumped to conclusions earlier when I said that I was kicking the can down the road because actually finding this B vector appears to be exactly the same as solving this, but that's not quite true. I just need to find any solution. I don't need to find all of them, I suppose. So how do we find the basis? Okay, how to find basis of null space of a matrix. Math is power for you. That's a great channel name. All right. Hmm. Yeah, it was a good video. Uh, some of these channel names: Math is power for you, Engineer for free. You gotta admire them. Wait, what? The second row tells us x3 equals minus x. Oh yeah, because their sum is equal to 0. So the general solution is that, whatever, fine. The null space of A consists of all vectors of the form x above. The dimension of the null space is 3. We need 3 independent vectors. So what we can do is take x and split up as follows. Yeah, all the a's, all the c's, all the b's. Each of the column vectors above are in the null space of A more over their independence, thus they form a basis. So it looks like there's a trick you can do here. You can take the RREF and just read the null space basis from it by negating everything except for the ones, which I'll have to read this more carefully to understand it, but reducing the matrix A to the reduced row echelon form results in blah. There are 3 pivot columns corresponding to the pivot ones in red. I still have no clue why anyone in their right mind calls these pivots. Anyway, we're just stuck with the term. Anyway, pivots ones in red and the rank nullity theorem, I don't care about that. Vectors corresponding to the free variables, fine. In other words, this guy's free, that guy's free, that guy's free. At this point, it's worth remembering where all this comes from, the homogeneous system of linear equations, ax equals 0, which has now been reduced to all this junk. Yes, that's right, yeah. Expressing the pivot variables in terms of the free variables. Oh, actually it was simpler than I thought. Because if I take each of these equations and pull all the stuff to the right-hand side, which is what I did here without realizing what I was doing. Where did I do that? Over here. Or maybe over here. Yeah, you see minus b, minus c, minus e. But then there's one more step that I didn't get on my own. Shows the way the basis vectors of the null space of A will be filled in from their skeleton form simply by indicating the column where the free variable in question is located. I don't understand. This is the step I don't understand. Expressing immediately shows, yeah, well, maybe for you, but anyway, expressing the pivot variables in terms of the free variables, we have this. So these are the non-free variables. And therefore, 1x1, wait. Yeah, 1x1 wait. It will be filled in from their skeleton form by simply indicating the column where the free variable in question is located. So The null space of A is solution x equals 0. To find the scheme, I take the augmented matrix. Suppose after doing this you obtain blah, which is not the matrix given in the question, which makes things more confusing, but whatever. Now look at the columns that do not contain any of the leading row entries. So that one, and that one. These columns correspond to the free variables. Note that at this point, we know the dimension of the null space is 3 since there are 3 free variables. The free columns in question are 2, 4, and 5. We may assign any value to their corresponding variable. So we set blah, blah, and blah, where they're arbitrary. Now let's solve for x1 and x3. Well, x1 has to be equal to negative x5, and so on. The second row tells us that x3 is equal to negative x4. Okay. Oh, sorry, x1 is equal to x5. And the first row tells us x1 equals x5. So the general solution is blah. The null space of A consists of all vectors x of the form above. I feel like I've almost got it. The null space of A consists of all vectors of the form x above. The dimension of the null space is 3. We need 3 independent vectors for our basis, so we can split it up like so. Each of the column vectors above are in the null space of A. Moreover, they are independent, thus they form a basis. I'm not sure if this answers your question. No, it doesn't. I want to know why it's the case that you can just grab these vectors so I'm struggling at the step where it goes from me just fiddling around with algebra until I get it to an actual algorithm that you could write down in the computer. I'm still trying to figure that out. Maybe this is just unhelpful and I should look at something else. the column space has the basis blah blah and blah. XYZ is in the null space if and only if blah, that is equivalent to the four equations blah 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 from minus y equals 0, of course y equals x, so the other three equations can be written. It's not an algorithm. This is just filling with algebra. Oh, this is the one I was just looking at. All right, maybe I should use different search terms. Algorithm for null space basis. Hmm. You should look at this one again. So those are the free variables. And therefore, the linear combination it is worth remembering have been reduced to this. Expressing the pivot variables in terms of the free variables, we have that. Immediately shows the way the basis vectors of the null space will be filled in from their skeleton form, simply indicating the column where the free variable in question is located. this last one is all zeros, because the last row of the REF form is all zeros. Which means that each of these lines gives us one basis vector for the null space. So I keep my free variable, I give that a I don't get it. So from this 3, 4, 2, 3, 4, 2. I don't understand why I'm having so much trouble understanding this right now. Like, none of this is complicated, but I'm just not seeing the light. Maybe it is complicated. So yeah, so I'm still trying to figure out what this T is. And this T is the columns of the null space, or the columns of the basis of, or the basis of the null space. This T is the basis of the null space. And how do I get that? This is my RREF matrix. It's actually not RREF because I forgot to normalize this and get rid of that. So let's actually do that. Let's do that. And then here, then we can add that. So this becomes 0, this becomes 8, right? I guess we could also do that. I hope that's right. Let me just quickly, this, yeah. Yeah, okay, so that's the RREF. And so we're looking for vectors that when you, now wait a minute, because, wait a minute, this right hand side doesn't matter if we're trying to find the null space, right? Right? So I have one I have one, no, I have one free variable. Whoops. I have one free variable, which is this, right? I have two determined variables. So this doesn't matter. We don't care about that. It makes no difference to us. So man, parameters now. Maybe I need to look at this more carefully. So expressing the pivot variables in terms of the free variables. 1x1 is equal to this expression, 1x3 is equal to that expression, and 1x6 is equal to 0. And what happens if I do that? I get 1x1 is equal to negative x3, and 1x2 is equal to x2. Oh no, 1x2 is equal to 0? Yeah, that's right. 1x2 is equal to 0. So that pivot variable x2 is 0. Right? So, or I guess I'm calling this x, y, z. So this y is forced to be 0. Z is free. So then what is x? X is equal to minus z. We kind of already knew this. And then what does this person say? I don't understand how they got this. There's a step missing here. Okay. X2 what? So minus 3x2 I don't get it. I don't get it. Carlton, that's in Halifax. It's in Ottawa, right? Reduce row echelon 4. Recall that we can get the solutions to x equals 0 by setting the free variables to distinct parameters. Then the set of solutions can be written as a linear combination of n tuples where the parameters are the scalars. These n tuples give a basis for the null space of A, hence the dimension of the null space of A, called the nullity of A, is given by the number of non-pivot columns. We now look at an example of finding a basis for NA. Let A be that thing. We perform the following elementary row operations, bunch of stuff, to finally obtain this guy. To obtain all solutions for x equals 0, note that x2 and x4 are the free variables. X2 and x4 are the free variables. Yes, because there's an implied row of all zeros under here. Setting x2 equals s and x4 equals t, then all the solutions are given by x1 is equal to, flip all these signs, s minus 2t. And this is given as t. And then for the pivot columns, or sorry, for the free columns. So for the pivot, okay, so this s and this t, that's because we chose these as our free variables. Remark, note that one could have obtained directly the first vector by setting x2 equals 1, x4 equals 0, and then solving for x1 and x3, and the second vector by setting x2 equals 0, x4 equals 1, and solving for x1 and x3. In general, if A is an REF, then a basis for the null space of A can be built up by doing the following. For each free variable, set it to 1, the rest of the free variables to 0, and solve for the pivot variables. The resulting solution will give a vector to be included in the basis. Okay. If we had set s to 1 and t to 0, oh. So the idea here is we know that the null space has dimension 2. And we know that the pivot variables are determined by the free variables. Therefore, we can choose the simplest possible basis that we want by doing an orthonormal basis over the free variables. And because the pivot variables are determined by the free variables, okay, I think I'm finally starting to understand here. So if I go back here, I say, okay, choose orthonormal basis over the free variables, which in this case is just 1, because we've only got one free variable. And then how do we figure out the pivot variables from the free variable? We just read it from here and put the negative on it. Yeah. So we read what's above the pivot variable and put a negative sign on it. So finally, at long last, you can just say this is -1, 0, 1. Okay, so let's check. Is this -1, 0, 1 in the null space? Yes, easily, obviously, because that column minus that column always gives us 0. Okay, now this B vector, where did I get that again? If I choose, okay, let's choose x, y, z equals 1, 2, 3, for example. Is it the case that t times x, y, z plus b times s equals v? Well, I don't know, let's just call this, well, whatever, let's just go. So t wait a minute. Oh yeah. So we're choosing our free variable. Well, of course. Yeah, okay. So does 740 satisfy this? That's all we care about. Well, 7 times 1 is 7 plus 4 is 11, so that doesn't work. So where do we get this b again? Was it this right here? Oh. Where did I get 740 from? Anyway, let's put 8 minus 1, 0 and see what happens. So if I plug in 8, subtract 1, I get 7. 8 times 2 is 16, plus 2 is 18. 8 times 3, oh yeah, that does work. So that's it. We did it. Problem solved. Yeah. Yeah, problem solved. So this is the basis of the null space, and then this is just any arbitrary solution. And what's this particular solution? Where does that come from? It comes from setting where did that solution come from? Oh, it comes from the fact that the pivot variables will form an identity matrix. And that we're setting all the free variables to 0. I guess. Yeah, because here in this right-hand side, we're gonna, we know that z is free because, so okay, these expressions here are for the homogeneous, I'll just put and then this thing here is I think this is what happens if you set all the yeah, okay, it's a solution because you do get a unique solution if you so there's one free variable and two determined variables, so it's just a solution that you get. Yeah, solution obtained by setting free variables to 0. Okay. Now here's something really interesting that we can do. Earlier I chose the orthonormal basis over the free variables, which is fine. We can do that. Yeah, well, yeah. But it would be nice if, so there's one last step here. So one last step, right? We would like to determine the pivot variables from a I guess I'll say geometrically meaningful point instead of arbitrary values for the free variables. In other words, yeah, I just have this one z free variable, but it doesn't mean anything. It's just some scalar multiplier in front of the column space. It has no meaning. But what would be nice here is here, this is not something we can enforce. This, not in the way I've done it here anyway. But what we would like is that ABC be some function of mx, my, mz. Right? Well, hold on though. We can just set that, can't we? I mean, they're free variables, aren't they? I think at this point I have enough to go on, and we just need to try it. The first thing we need to do is write a function to do reduced row echelon form, which is not simple. By no means is that simple. It's one of those really annoying programming tasks that's very error prone and easy to get wrong, and it's made even more complicated by the fact that with floating point numbers, we have to worry about like extremely tiny numbers that are supposed to be 0 but are just like, because of floating point error, like they're like 1e minus 30 or something. You got to worry about stuff like that. And also there's this notion of pivoting. All right, let's try and figure that out too. Gaussian elimination with pivoting. Oh, it's a little too big. Yes, yeah, exactly. This division by 0 or near 0. Yeah, so example, blah. And another example here, maybe it's not 0, but maybe it's very close to 0. A is full rank, the solution is in its unique form, the augmented system, blah. Subtract blah, 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 will not work because there is a 0 in the pivot location, A22. Yeah. Swap second and fourth rows of the augmented matrix. Continue with elimination, blah. Another 0 has appeared. Swap. Another example. With naive Gaussian elimination, we get that. Solving for x1, x2 using exact arithmetic, we get that expression and that expression. However, using finite precision floating point arithmetic with epsilon equals 10 to the minus 20, x1 equals 0, and x2 equals 1, y. I gotta think about this. So here we get a 0. That makes sense because we're just going to overwrite 0. That's just always the next step in the algorithm. And then here all we would have done is computed 1 over this number and then subtracted it times this. So 1 times 1 over epsilon is 1 over epsilon subtracted from here. And then I guess oh, I see. This number just becomes exactly 1. Oh, no, this number is huge, so we get a huge number. Whatever, let's just keep reading. Partial pivoting is usually sufficient. Okay. To avoid division by 0, swap the row having the 0 pivot when the row is below it. To minimize the effect of round off, always choose the row that puts the largest pivot element on the diagonal. Okay, fine. Pivoting, that is row exchanges, can be expressed in terms of matrix multiplication. Do pivoting during elimination with track row exchanges in order to express pivoting with matrix P and P zeros. Yeah. Interesting. Partial pivoting is usually sufficient. Consider this. With partial pivoting, the first row is the pivot row, and for large C, that 1 goes away. Yeah. So the pivot is selected as the largest in the column, but it should be the largest relative to the full submatrix. Yeah, okay. Yeah. I think I'll be okay with partial pivoting, because well, really that's just wishful thinking. I can't actually justify that. Yeah. Consider a 2 by 2 system describing 2 lines that intersect. The matrix form of this equation is blah. The equation for 2 parallel but not intersecting lines is blah. Here the coefficient matrix is singular. I don't know what a coefficient matrix is. And the system is inconsistent. Well, yeah, the rank is 1. For 2 parallel and coincident lines is not. For 2 nearly parallel lines is that. Consider the solution of the two-basis system where b equals that. One expects the exact solutions to ax equals that, and ax equals that will be differentially solutions v. Yeah, because of floating, yeah. A lot to, interesting. Oh yeah, norms. Well, yeah. This is actually a good slide deck. I'm not reading it in detail. I'm just trying to get the idea. Interesting. Yeah. Okay. This is a really good slide deck. Who is this person? T. Gambill. CS357. Oh, the... Maybe I'll click the big shiny button. Oh, hey. That's interesting. That's really interesting. Is T. Gambill in here? Oh. Wow, this is actually a pretty nice looking course. Yeah, University of Illinois is pretty well known. Well, at least at Urbana-Champaign. I don't know if there's other less good campuses, but whatever, yeah. Anyway. Oh yeah, see, Urbana-Champaign. I thought it was Champlain, but it's actually Champaign. Go figure. 2011. That was over 10 years ago. Scary. Anyway, I got distracted. What is it I was trying to do? Oh yeah, well, I was trying to figure out pivoting. Yeah, I think we're going to stick with partial pivoting. So... I guess let's just try it. Well, it would be nice to use... Okay, I am doing this project in Unity. I might show you the Unity thing I've started. Unity, Gaussian elimination. There's got to be someone who's already written this. C#. So, I don't know. ads on this site. Let's put in my example one and just see what it does. What was my example here? Hello. So 1, 1, 1, 2 minus 2, 2, 3, 3, 3. Ooh, it doesn't like that. Man, it would be really nice if there was just a routine I could use that implemented RREF, because I can do everything else myself. But I really do just have to write it, I guess. Oh, what am I doing? Of course. Yeah, I definitely want it in 360 assembly. C#. Oh, why would you do this? Just, oh my god. Oh my god. Ugh. Okay, actually, I'm kind of curious. What does the J implementation look like? Man, J programmers are a different breed. Anyway, swap row, blah, blah, R1, R2, and... Okay. Yeah, so I need to put it in RREF. Okay, if I just had an upper triangular matrix like this, is it still simple to create the null space basis vectors? Yeah, isn't it? I need a better example if I want to try that. So let's do, I just need another example of, so 1, 2, 3, 4. I guess I'll do 1, 1, 1, 1. Then I'll do 2, 3, 4, 5. And 2, 4, 6, 8. Well, actually, let's make this a little more interesting. I'll put it in here. And I guess I'll do 5, 7, 9. So I intentionally created this row and this row to be linear combinations of this row and that row. And why not? Let's give ourselves a vector on this side of, I don't know, 2, 5, 6, 7. And, I mean, let's just do it, right? So, and we're going to pretend we're a computer doing partial pivoting. So, the first thing we do is, actually this is already correct for partial pivoting. So then what do? We, oh, I'm gonna run into bad numbers here. Shoot. You just go ahead and do this. Just to keep things a little more manageable. And then this. So first I divide this by 3. And we get this, which should come as no surprise to anybody. And then we subtract all the multiples on all the rows above and below. But what if we don't do the row above, and we just do the rows below? Well, I guess let's just see what happens. So here we get that. Here we get that. This is going to be 0. This is going to be -1. This is going to be -4. Oh man, I'm running into trouble now. And this is going to be, no, -2, -3. Whatever. It's okay. I know what I mean. And then here, this is going to be 0. This is going to be -1, -2. -3. Right? Yeah. Okay. And then the next step is pick. Oh wait, what am I doing? Wait. This is not. No, I gotta restart. So here, this is already, the division's already done. And then here we're going to subtract the first row from all the others. This happens no matter what. So let's just go ahead and do that. So we subtract 3 times, so this is actually just going to be all 0. And actually this is going to end up being 0 as well, just by fluke. And then here we're going to subtract 1, so this is going to be 0 minus 1 minus 2 minus 3. This comes out to 4. And then here we subtract 2 times that row. So we have 0 minus 1 minus 2 minus 3. And here we have 3. Then we do a partial pivot here. So we take the largest in magnitude, so we may as well use this one, which is what I would get the computer to do probably. So this becomes minus 1 minus 2 minus 3. This is all zeros. The 4 comes up here. 0 goes down there. And then here we divide by -1 to get this. And then now here, normally, if you were doing this, you would also subtract upwards, but let's not do that right away because I want to kind of see what happens. So now let's subtract downwards. So we don't do anything to that 3rd row, and then for the 4th row we add 1 times, and we just get this. Here the fact that this is all zeros and -1 means that there are no solutions, so let's just arbitrarily change the problem such that there are solutions. Okay. So here we have 2 free variables, and we have 2 forced variables. Now this is our solution to, if we set, this is just a solution to this matrix. So if I do 2 times 1 minus 4 times, wait a minute. Did I make a mistake somewhere? Oh, yeah, that's because I didn't subtract upwards. So this actually, okay, I see. This isn't the solution because this is not the identity matrix. Do you see? So let's just go ahead and do that right now. It's not done in the order that the computer would do it, but that's okay. You see, this is why I wanted to do it by hand, because I wanted to understand this concept, right? So we're going to subtract 2 times that, so this gives us -1, and this gives us -2, and we're going to subtract 2 times that, which gives us 10. Okay, now, 10 times 1 minus 4 times 2 is 2. 10 times 3 minus 4 times 6 is 6, yep. 10 times 1 minus 4 times 1 is 6. 10 times 2 minus 4 times 3 is 8. Yes, okay. Yeah, okay, so this does work. So that's why we do need to subtract above and below the diagonal. Fine, no problem. We can do that. And since we are going to the trouble of doing the complete reduced row echelon form, then I know that the basis space of my or the basis of my null space is just so if I pick one of my bases to be 1 for this free variable, well, 1 for this free variable and 0 for this free variable, then now how did I understand this before? I'm just putting myself through the logic here. Oh, yeah. Because we have that in the homogeneous solution, 1 times that plus 0 times that minus 1 times that minus 2 times that equals 0. So, yeah. So we get that this guy, x1, is equal to negative 1 times this guy, because it gets subtracted to put on the other side of the equation. And we're not done with that equation. We also get that it's equal to, yeah. I can't explain it orally right now. I'm satisfied that I can do it, that this works, and that it makes sense. I'm just struggling to explain it out loud. I'll have to figure that out. But here what we have is, this is our B vector, and our T is, what we do is we just put an identity matrix here and then negate everything else, right? That's what we're doing. So we get 1, 2, minus 2, minus 3, 1, 0, 0, 1. This is our T, right? So if I take either of these columns and multiply it by this matrix, I should get 0, right? So 1 plus 3 minus 2 times 2, good. And then same thing, 1 plus 1 minus 2 times 1, 2 plus 4 minus 2 times 3, yeah, that all works. Then this one, 2 minus 3, 0, 1. 2 times this plus that is 6 minus 3 times 2 is 0, yeah. I still am fuzzy on this. I'm still fuzzy on this technique of doing this trick. I kind of get it, but not really. But I'm satisfied that it works, you know, so I'm just kind of gonna move on. Well, am I satisfied that it works? Why should it be the case that, right? Because, okay, let me write out these equations here. So we have x1 minus x3 minus 2x4 equals 0. This is for the homogeneous equation. And we have that, oh, well, I guess I should x2 plus 2x3. It looks like 2 times 3, but this is an x. Hey, now wait a minute. That's autocorrecting it. Hey, did you see that? Anyway, whatever. Whatever. I don't care. And then plus 3x4 equals 0. So why should it be the case that if I take this column vector, that multiplied by the original matrix, I get 0? I don't understand that at all. I kind of understood it from that basic HTML page we had open earlier. If I set x3 equals 1 and x4 equals 0, then we get that x1 equals 1 and x2 equals minus 2. So that is where this 1 and minus 2 come from. Oh, wait a minute. Because these are the coefficients on x3, but in the position of the equations for x1 and x2. Okay. Yeah. Okay. Yeah, and it's very important that this actually be an identity matrix. Otherwise, this wouldn't work, right? Because you'd have to divide by that coefficient. Yeah, okay, I get it now. Okay, I'm satisfied. Okay, great. Let's actually finally code up Gaussian elimination with partial pivoting. And let's not worry about speed. The only thing we do need to worry about are these, corner cases, right, where a row might turn out to be all zeros. So I think what we'll do is, if when doing the search for the pivot, we find that there's no value greater than some minimum threshold, then we'll just assume that it's 0. And that minimum threshold should probably be I don't know. I'll think about that. Let's just use that, arbitrarily use 1e minus 8 for now for that threshold. I'm just making that up. Yeah. So, this is what they already have in there. That's nice, I guess. Set up and draw. Yeah. Okay, well, let's just leave that in place here, because first I want to just write Gaussian elimination. So I guess we'll take in a 2D array, like an array of arrays. That seems reasonable, right? Don't you think? So var g this how you write it in JavaScript? Function of mat. I'll just say A and B, which are the classic names. Return 6, I don't know. That seems like, okay, fine. So var r is equal to a dot length. Var c is equal to a 0 dot length. There are assert statements in JavaScript. Okay, thank you. Okay. And yeah, let's do that. Oh, I'm getting a phone call. I gotta go.